Hi, I'm Corné van Dalen and this is a Control Systems 344 summary video. Throughout the course of this module, I will regularly bring out short videos like this one and they will summarize the important concepts of this module. Please note that they are only meant to provide you with a starting point to master the material, not to replace lectures or the textbook. Today's video is an introduction to state variable modeling of dynamic systems. In the classical control approach of Control Systems 314, we describe the dynamics of a system using transfer functions. The modeling process consisted of the following steps. Step 1. Derive the differential equations for the system. 2. Transform the differential equations to the Laplace domain. And 3. Rearrange things to get the transfer function. We then use the transfer function to analyze the system dynamics and design a controller. Let's look at a simple example. Consider an object with mass m experiencing a force F and viscous friction with coefficient B. The output is the displacement Z. Step 1. The differential equation is given by Newton's second law, where the sum of the forces is equal to the mass times the acceleration. Step 2. This is the differential equation after applying the Laplace transform. And step 3. After rearranging terms, we get the following transfer function. In contrast, in the modern control approach of this module, we stay in the time domain and describe the dynamics of a system as state variable equations. The modeling process consists of the following steps. Step 1. We start at the same place, deriving the differential equations for the system. Step 2. We then choose a set of states and define the state vector x. And lastly, we manipulate the differential equations to write them as the following two matrix equations called the state variable equations. The first equation is called the state equation and the second equation is called the output equation. In these equations, x dot is the derivative of the state vector, A is a matrix, x is the state vector, B is a column vector, U is the input, Y is the output, C is a row vector, X is the state vector again, D is a scalar, and U is the input again. The state variable equations therefore describe the dynamics of a system as a set of first order differential equations. Let's look at the example again. Step 1. The differential equation is the same as previously. Step 2. For this example, we choose the velocity z dot and the displacement z as the two states, and the state vector is therefore given by this column vector. The state variable equations should now have the following form. To fill in the top row of the state equation, we manipulate the differential equation to get this equation, and we now fill in the elements. For the second row of the state equation, we write down the trivial equation x dot is equal to x dot and fill in the elements. Sorry, that should have been z dot is equal to z dot. For the output equation, we write the output in terms of the states and the input and fill in the elements. These state equations now describe the dynamics of the system.